of which we will cover 6.1 and 6.2 this week. We will cover 6.1 in this lecture. It's going to take us a little while to get through it. Okay. Good stuff, though. Still integrating, and this is section 6.1. I didn't check the volume. Did y'all see, was the volume okay on that recording? I should look at it real quickly. Testing, 1, 2, 3, it's good. Okay, so here we're talking about volumes, finding the volume of something three-dimensional. And there's more than one way of doing it. One way is what they refer to as slicing, and the other way, we're talking about it as rotations. Okay, we're really going to spend a majority of our time talking about the rotations. And when you're dealing with the rotations, there's two parts to this. There is a disk method in finding the volume of an object as it's being rotated around an axis. And then there is also a vector method. Okay, so just trying to keep this all organized, you're slicing, and then you're rotating, and when you're rotating, you're using two methods. One is which is known as the disk method, and the other is known as the washer method. When you start doing rotations, we're going to be talking about a circular method of finding the volume, and so in here, you're going to see consistency with pi r squared. So we're going to heavily use that area is pi r squared when we're talking about the rotations, which is really close to 3/4 of this section. So just kind of, again, a really quick way of just kind of preparing for what's about to happen in this section. Now, just as a little bit of an introduction, I'm going to go to the textbook and talk a little bit about what volume is. When we start talking about volume, we're really thinking of length times width times height. You're multiplying three dimensions in order to get the volume of a three-dimensional shape. Now, when we're doing length times width times height, and we're going to find volume by using integration, width is really going to be like our dx, where our dx is where the width is getting so increasingly small for the object that we approach zero in the width and the partitions of all the area or the volume underneath the curve. So what happens is then we kind of look at length times height as being the area, and then dx being the width. So our volume becomes more area times width, which is that third dimension, which ultimately is equal to volume. So we're going to be looking at stuff like this. I'm going to now turn into my textbook to page 396 to kind of let you see something here. Well, if I can find page 396, that would be nice. Okay. I can read a little bit of an introduction. This is not right. That's what I get for using more than one textbook when I'm trying to get this stuff prepared for you guys to make it as easy as possible. Okay. That is all wrong pages. It's page 308. Good grief. All right. Okay. Volumes using cross sections. In this section, we define volumes as solids using the areas of their cross sections. So if you have some three-dimensional object and you slice it, then you're looking kind of at the area, that surface area of that slice, and then you're multiplying it times its width to therefore give you volume. So we take a cross section of a solid. In the plane, what does it say? A cross-section of a solid S is the plane region formed by intersecting the plane. We present three methods of obtaining this cross-section appropriate to finding the volume of this solid. The method of slicing, which I've just kind of put in the title, the disk method, and the washer method, which are both involving rotations. So we're looking for volumes of these objects, and as I said, you're looking to find volume by considering the area of the face of the slice that you're taking multiplied times the height, where we're going to come up with the dx as being one of the height or width or length pieces of this process. So just kind of getting a vision of all this. So then what happens is to find volume, if we're talking about volume now being considered area times width, which our width is like our dx, then we start looking at volume using the methods of integration, and volume becomes integration of area times dx, which means you're taking all these slices, the volumes of all these slices, and accumulating them or adding together under the method of integration. So it starts looking like the volume of this three-dimensional object is integrating the area times the width. And so this, if we look at it in terms of x, was what they refer to as a of x times dx, which you'll also find in a box on the adjacent page in the textbook right here. The volume of a solid of integrable cross-sectional area AX is given here. So here it is showing back the summation. If you sum up the multiplication of all the areas times the widths, it converts to integration as the width approaches 0 of each slice. So then what you're kind of looking at is some three-dimensional object, and you're slicing it. They do a really good job. Here he talks about it up here as referring to these slices as thin slices of loaf of bread, where you take the volume of each slice. So it's a really good description, and several textbooks will refer to this as looking at slabs or slices of the three-dimensional object as pieces of a loaf of bread. So then they'll go in and they'll say, tell me the volume of this three-dimensional object. So you're going to go in and look at it as slices. You're going to integrate it as area times width to come up with the volume. They also do a good job here of trying to give a basic procedure or steps you would use to come up with these volumes, and I'll write this procedure down for you just to kind of get an idea of how to start. Okay. The first thing you want to do is they're going to give you a curve and usually the equation of the curve and some boundaries as to what you're going to be rotating or where you're going to be looking for volume. So you want to go in and make a sketch. It doesn't have to be a perfect sketch, but you need to have a good vision of what you're trying to get the volume of. Once you create a sketch, just like I said, a relatively rough sketch, then you're going to find your formula for area. Because remember, volume is area kind of times the width, the area of each slab or each slice times the width of each slice, which is going to be our dx. So you're going to go in and find a volume for, or find a formula for the area. Usually when you do this, your equation of your curve is going to be involved. Not always, but is often involved here. Then what you're going to do is, since you're going to have to integrate, when you integrate, you're going to have to be very careful that you determine appropriately what the upper and lower limits are of the integration. So when you're integrating your area times dx, this upper and lower limit, a and b, you have to be very careful in determining what those values are. So when you integrate, be careful in determining your lower and upper limit, determining a and b, these limits. Okay? Sometimes that means you have to find the points of intersection of your curves. Sometimes you can just look on the x-axis and define this. Sometimes you have to change it from x variable to y variable, but you have to be very careful. If you're integrating with respect to dx, then the upper and lower bounds must be x values. So if you're integrating with respect to x, your upper and lower bounds will be x values. But if you're integrating with respect to y, which we'll do a little bit of this, which kind of gives a little level of difficulty, then these upper and lower limits would be y values. So you have to be paying close attention. Am I integrating with respect to x, or am I integrating with respect to y in everything you do with these questions? Once you have your integration set up, you figured out what your upper and lower limits are, you figure out what you're supposed to be integrating, then of course you go in and integrate to find the value for the volume. Now when you integrate, there's going to be a lot, when you're inside your integration, they're going to have you use your ability to integrate by substitution quite a bit. So at this point, it just becomes sheer algebra, and be prepared to be needing to use the method of integration or the method of substitution to be able to integrate. Some of them are pretty straightforward, but others you'll need to integrate, and they're pretty good to set them up, so using the method of substitution is straightforward and not another level of difficulty to make it harder for you. Okay, so that's just kind of a quick warm-up preview. What in the world are we doing? And it will be pretty smooth once we get in and do some examples. Now, the first examples we're doing here are just even a little uncomfortable to me because I don't ever remember doing them to any great length in my history. So we'll look at this briefly, and if you're a little bit confused, it's because it does seem a little strange in the beginning, and then it will definitely improve as we move on. So the first thing we want to talk about in this section, if you again look at the title, is to find volume by slicing. So this is what we're going to look at right now, is to find volume by slicing. Okay, volume by slicing. So to find the volume by slicing, again, remember, we're really looking for the sum of the volumes of the pieces of slabs. So the sum of length times width times height is going to give you the sum of the volume of every little slab you take out of the three-dimensional object, which ends up being the summation of your area times your width of each slab, which we're going to talk about as dx, or what used to be delta x, when Riemann was explaining these summations. Then this converts to integration of area dx, which does equal your volume. So all of this is taking us to the volume of this three-dimensional object. Okay, so I'm going to use these examples directly from the textbook because they give me good diagrams, and I am not good at sketching these diagrams. So I'm going to look at example 1 in our textbook on page 398, so we get a nice figure here. And here we're talking about the volume of a pyramid. Let me look. Well, it's definitely not 398, is it? Where is this sucker? The volume of a pyramid. It's on the bottom of 309. Where am I getting these strange numbers? Okay. Why am I doing this? Must be my Stewart book. I like my Stewart book. Okay, here we go. Down at the bottom of this page, there it is. A pyramid 3 meters high has a square base that is 3 meters on a side. So if it's a square base, it's 3 meters on all 4 sides. The cross section of the pyramid perpendicular to the altitude, x meters down from the vertex, is a square x meters on a side. This is a really, in my opinion, awful question, but they consistently do this. Find the volume of the pyramid. Okay, this is like, what in the world are they talking about? Okay, so let's look at the pyramid over here, okay? Most questions, get back up your microphone. Most questions are not quite so this, and their presentation is this. They get better, I promise. Okay, so here is a picture in figure 6.5 that shows this pyramid whose vertex is at the origin, who has a 3 by 3 base, and so looking at 3 dimensions, this flat surface is really cutting through this x value of 3. Okay, so we're looking for the volume of this pyramid. So if you look at a cross section, as you see it in pink here, remember every cross section is going to be a different size, and so integration is taking good care of our different slabs or different slices of this pyramid. So the goal is to find a formula for the area of the face of this slice and then multiply it times dx, which is like the width. So we have the 3 dimensions, which will take us then into volume. So this is very difficult for me to sketch, but I will try because I know you need to also get this on your piece of paper. So you have your XY axis. You're getting ready to see it. Okay. And you're out here somewhere at 3. Oh, boy. Okay. So here's one side, and here's the other side. Coming down like so. There's one. I just do not do this well. I'm trying. Oh, my goodness. Oh, God. I'm anything but an artist, okay? See there, I told y'all this is hard for me. I just don't do this well. This is really bad. And to add to it, I'm doing it in pen. That's a little better. Okay. Something like that. All right, so if you're looking for volume, your standard setup is to integrate your area dx. And you know that if this is dx, this upper and lower limit must also be in x values. So you're going to integrate from the origin out to this 3 because they said that the height of this pyramid was 3 meters. So you're integrating from 0 to 3, which are your horizontal or your x values that you're looking for slabs or slices of this pyramid to find the area as it slides between 0 and 3. So now, to figure out what in the world area is, my diagram is so bad. I hope y'all did better than me. So here it is. It looks so much better in the textbook than I do it. So they show that this is every slice will be a perfect square. And every side of the slice will vary as you cut different slabs. So you let each side of your square be length x. So therefore the area of this, the face of this slab is what? X times x, which is x squared. So the area of every slice is going to be length times width of each square, which is x times x. So your area is length times width, which is x times x, which is just x squared. Okay? Now, again, the reason this equates to volume, we're focusing so much on area. The reason this equates to volume is because this is area times the width, the tiny, tiny width of each slab or each slice we cut, which then gives me volume. So the volume of that pyramid, who has an altitude of 3 meters, is going to be determined by integrating from 0 to 3 of x squared. And then you just go ahead and convert this to integration, which is really quite easy. And that just turns out to be 9. Now, they're really not pushing the units too terribly hard in this section, but this should be 9 cubic meters. If this is going to be a volume dimension or a volume amount, it must be in cubic units. And so that will be 9 cubic meters. Okay, let's try another example. What an awful picture I did. I will do better. That's not my worst one. Okay, let's look at example 3. Let me look at the book on page 310. Actually, it's example 2 on page 310. Okay, this one I won't be able to diagram this. This is terrible. This is a beautiful picture, but this is crazy. I can't do it. I do better with the rotations. I diagram the rotations or sketch them very well, okay? Just be patient. Okay, look at example 2, which is referring to this lovely diagram right here. Okay. It's a wedge, right? If you visualize a cylinder, okay, like the cardboard inside a roll of paper towels or something, okay, you have a cylinder like this one down here. Okay, you have a cylinder like this. And they've sliced it at the bottom, so the bottom is flat, but you're only seeing half of it. And then they take another slice at an angle. Okay, if they cut another slice at an angle, then you would have a wedge underneath my finger in the green plane that's cutting that cylinder. Okay, so that's what you have in this diagram, is a horizontal slice, which is the green one, and then another slice at an angle which forms a wedge, which can be seen kind of underneath my finger, which is what they have in this diagram. Okay, so it says a curved wedge is cut from a circular cylinder. The original cylinder was of radius 3. You're cutting the cylinder by 2 planes. One plane is perpendicular to the axis of the cylinder. The perpendicular plane would be like this green plane, okay? It's perpendicular to the axis of the cylinder. The green plane is perpendicular to the axis of the cylinder. And the second plane crosses the first plane at a 45-degree angle at the center of the cylinder. So if I cut another plane at 45 degrees to the center axis of the cylinder, then I would come up with this wedge. Okay, that's how they get the wedge. Now it says find the volume of the wedge. And you know, they don't go in, they should tell you more in the question. And later they do tell you a little bit more. They give you a little more hints. If the radius of the original cylinder was 3, let me grab a pencil. Oh, gosh, if I can do this. Okay, this was something of the original base of this cylinder. Okay, if this radius of this original circle that formed the base of the cylinder, then the equation of this circle at the base here would be with radius of 3, x squared plus y squared equaling 3. So the base of this cylinder has an equation of x squared plus y squared equaling 3. So equaling r squared, which is 9, 3 squared, which is 9. And so they talk briefly about this right here. Come on, light, focus. Okay, x squared plus y squared equaling 9 is the equation of the circle of the base of the cylinder. Okay, so here we have it. So this circle at the bottom, every point along this circle will have an ordered pair x, y, where y will be taken from x squared plus y squared equaling 9. So if you solve this, y would equal the square root of 9 minus x squared. Okay, and they show the negative here because of the quadrant at which this is showing, but you're not required to use that negative when it comes to actually formulating the area. So now, when they take slices and integrate with respect to dx, when you integrate, in this case, you're going to integrate from an x value of 0 to an x value of 3. So you're integrating from 0 to 3, and you're taking slabs all along inside here. You're getting these rectangular kind of brownish regions as you slice this wedge from an x value of 0 to 3. So when you integrate, they get easier than this. Okay, y'all don't choke on me here, okay? They get easier, I promise. These seem like they start really hard. You're going to integrate from 0 to 3 an area amount dx. This area is the area of each slice. And each slice, according to this diagram or this figure, each slice is a rectangle. And those rectangles they have in there, inside the wedge, okay, these rectangles inside this wedge, all right, will have, wish I could get this on the camera, these rectangles in here, okay, will have a vertical height here of x, and this point is on the base of the circle. So this point is x, y, which is x square root of 9 minus x squared from the circle. Okay, the bottom point of each rectangle. So if you're looking for the area of the rectangle, well, if I explain this now. If you're looking for the area of the rectangle, it is going to have to be this length times this height. If this is x, that is your, I hope I'll get this backwards, that will be like your height. No, that's not right. Let me look at this for just a minute. Yeah, that is right. Okay, so if your area is your height times your length, and this point here is x square root of 9 minus x squared, your height is actually the x value. This is kind of hard to see. And your length is twice the square root of 9 minus x squared from that x-axis. Okay, your height is x, and this length from this point to the circle itself, each one is square root of 9 minus x squared. So you have to double it. Really, it does get better than this, I promise. It gets a little easier. When we get into rotations, it gets a whole lot easier. So that is the area of each slab as x changes values as you slide this rectangle inside the slab between 0 and 3. So to find the volume, your volume is to integrate your area dx, and now your area is 2x times the square root of 9 minus x squared dx. And that is algebraically what you must integrate to get volume. So when you do this, the only way you're going to be able to integrate this thing and turn it into just doing sheer algebra, how are you going to integrate this thing? That's right. So when you do this, you're going to let u equal the 9 minus x squared, and then du will be a negative 2x dx, and then it will flow quite easily from there. And we have a lot of examples to do, so I'm not going to finish the method of integration because to integrate this is not that bad. But your answer should turn out to be, I believe it's 18. Yeah, 18 cubic units. It doesn't say anywhere about being meters or whatever. So 18 units cubed is your volume. I really think that these are the harder questions of this section. When we get into the rotations, I think it will get easier for you. So it kind of starts out very hard, and then it lightens up a little bit when we get into the rotations. So let's go on now into the rotations. And when I create your homework, I'll create more homework on rotations to make it easier for you. Okay, so now we're going to look at solids of revolution. And there are two parts of solids of revolution. One is the disk method, and one is the washer method. So I'm going to call this part 1 because this is going to be solids of revolution using the disk method. Okay, using the disk method. Okay, so now I'm going to go into the textbook where there's a nice little diagram on page 311 and give you a little bit of taste of what's getting ready to happen. And this is actually, I can teach this to you very easily. You'll catch on pretty quickly. You're going to look for the volume of something like this, which in my opinion looks like a bullet. Okay, you're looking for the volume of a three-dimensional object kind of seen in this green figure. The way we do this is you start out with a curve like this one in blue, and you spin it around the x-axis. So you spin this blue diagram, you spin it around the x-axis, okay, which will form that bullet-looking object. Okay, so you're going to take a curve and start spinning it around either a horizontal or a vertical axis. When you do this, you want to find the volume. So if you start looking now, you're spinning it, which is creating this object. When you start looking at volume being area times width, all of your cross-sectional slices are going to be circles. So every time you're looking for the area of this cross-sectional region, it's going to be pi r squared, which is the area of a circle multiplied times the width to give you volume. So when we start spinning things, our slices are circles, which makes it a lot easier to compute the volume. So they start talking about the solid of revolution, so that the area is pi r squared of each slab. The surface area of each slab or each slice will be pi r squared, and the volume will therefore be that area of each slab times the width, which we're going to make minutely small, approaching 0, which is going to be discovered by integration. So when you start integrating your area times your width to create volume, you're really integrating pi r squared, which is the area of each circle, times your width. So this is called the disk method because this little kind of orangish, pinkish region here is a disk. So that's why they call this the disk method. So now what we're doing is we're finding volumes of disks. Oh, I need my pen. And they're going to be found by integrating from A to B, again, of your area, dx. But now your area is going to be easy to calculate by being pi r squared dx. But your radius, because you're integrating with respect to dx, your radius needs to be using the variable x, and so they redefine this one more time by calling this r of x instead of just r, because it has to be in terms of the x variable. Okay, so you're going to always write your radius as a function of x when you're integrating with respect to dx to find your final volume. Okay, so this, you can see, this is going to become a little bit easier. So we're going to look directly into some examples now. We're going to look here at example 4 on page 311 of our textbook. And it says, and I'll write a lot of this down for you, and hopefully this will become a little more black and white in your mind. These are so much easier for me to graph, and they'll be a lot easier for you to graph also. Come on, camera. Okay. So this one says what you're looking for is the volume of the region between the curve y equaling the square root of x, where x is between 0 and 4, and the x-axis revolved about the x-axis. Okay, so we're looking for the volume of the region which is created when you draw the curve y equaling the square root of x, limited between 0 and 4, and you're going to spin it around the x-axis. Okay, so let's get a diagram of this. Okay, here is y equaling the square root of x. From 0 to 4. We're going to stop at 4. Then it says, take this thing, the area, it says find the volume of the region created by this curve y equaling the square root of x between 0 and 4 and the x-axis. So it's also bounded by the x-axis between 0 and 4. So your region is between this curve and the x-axis between 0 and 4. Then they want you to spin it around the x-axis. So they want you to take that curve and spin it around this x-axis, which will create that shape that looks kind of like a bullet. Okay? So now, visualize picking a slice out of the middle of this thing, which will be a circle. And those slices are going to go from 0 to 4, and their width is going to be approaching 0 according to the limits and the methods of integration. So we know what we're supposed to do. We're supposed to be integrating the area of each slab times the width of each slab in order to determine the volume of this three-dimensional object. I'm going to do it with respect to x because I'm rotating around a horizontal axis. Now, my upper and lower limits are where are these slabs sliding from? They're sliding from a value of 0 to a value of 4 on this horizontal axis. So I'm going from 0 to 4, which are x values. Now I need to know the area of each of these slabs. Well, the area of each of these slabs is going to be a circle, so it's pi r squared. Now I can't put r there because I'm integrating with respect to x. So I need to figure out what in the world is r. Well, r is the height from the x-axis to the point on the curve. And this point will move along the curve as your slabs are being calculated around the curve. Well, if this curve is defined as y equaling the square root of x, then every point on this curve is x square root of x. xy, where y is the square root of x. So what is the radius of each one of these slabs? Square root of x. It's this height right here, which is the square root of x. The radius is this height, which is the y value, which is the square root of x. So you're integrating from 0 to 4 of pi times the square root of x squared dx. And this will give you the volume of that three-dimensional object. So you can pull the pi out the front, and this becomes what? Just x dx. So this becomes pi times 1/2 x squared, evaluated from 0 to 4, which turns out to be 8 pi units cubed. Okay, they're not showing that it's units cubed, but I'm going to kind of write that because I want you to really recognize that this is a volume amount. It is that simple. Okay. Let's try another one. Now, I'm not going to always integrate even this far, especially as they get to be a little longer in the process of integrating, because my goal is just to get you set up. Okay, so now let's look at example 5, also on page 311. Okay, and going through the procedure as we just did, you're going to read the question. It's going to seem kind of strange. You're going to sketch it, kind of get a vision, visualize this thing spinning around an axis, then set it up to find volume. Okay, example 5 says you have a circle. It says the circle, and it's very vague. The circle x squared plus y squared equaling a squared. This means that a is my radius. A squared is my radius squared according to the equation of a circle. This circle is being rotated or spun. It's going to be rotated around or about the x-axis. Okay, rotated or spun about the x-axis. And when you do, this will create a sphere. You start spinning this circle around, you're going to make a sphere. Find its volume. Now, since they're not giving me a number value for radius, they're leaving it as a, our answer is not just going to be a number. It's going to have the a in there so that you can do it for any circle of any radius. So kind of visualize this. Okay, you're going to have some circle of radius a. So I don't know. I'm just going to kind of sketch it as 3 little units out. But remember, it could be any value. Here is my circle. Okay, there's my circle. Now, I'm spinning it around, get the right axis, okay? We're spinning it around the x-axis. So it's rotating like that. It's coming kind of toward me off the page and then behind me. Okay, you're spinning it like a ring. You're spinning it toward me out of the page, and it's going to come back up the back side, which is going to create a sphere. Okay, be certain you're spinning it around the x-axis to get this vision. So now, this, come here, computer. Thank you. Okay, this is the radius of my circle, which is of length A. So I'm going to integrate from 0, well actually from more than that. I'm going to integrate from negative a to a, creating all of these slices, which are circles, inside the sphere. So maybe I should put one over here off. Oh, this looks bad, but it puts one over here off of the center. Here's another slice of a slab of this sphere. So I'm going to be integrating from negative a to a of the area of a circle times the width in order to come up with the value of the volume of the sphere. Well, each one of these slices is a circle, so it's going to be computed as pi r squared. But what is my r value? Well, my r value is the distance, the vertical distance right here. My pencil's trying to give you a sketch of that vertical distance from the x-axis to the circle, because each slab you slice out of the sphere is going to have a different radius. So this point right here, whose ordered pair, is defined as x and what? Your circle is x squared plus y squared equaling a squared. In other words, y is going to be the square root of a squared minus x squared, right? So this is x and the square root of a squared minus x squared. So you're going to be looking for these ordered pairs on these curve which you have an equation for. So when you're integrating and you need x values, what is radius in terms of x? There you go. The square root of a squared minus x squared, and that's all going to be squared. Remember, a is a constant. It's a number. So if you take a square root and square it, that's just going to be negative a to a of pi times a squared minus x squared dx. And when you integrate this, and I'm not going to take the time to do it, it's going to become 4/3 pi a cubed. And isn't that the volume of a sphere, where instead of a we usually put r? So try to visualize all these slabs, which I'm not doing a very good job of sketching these good slabs here. But you're really taking the area of each of those slabs multiplied by the width to give you the volume. You're adding up all those slabs in order to get the volume of the entire sphere. No, because pi a squared is all a constant, but pi x squared is going to be 1/3 pi x cubed, evaluated from negative a to a. Okay, so yeah, it's not going to be hard. Okay, let's look at another example. I've got a lot. It's the setting up of this stuff that's most important to get y'all comfortable with this. Okay, this is a little bit of a change. Okay, not difficult, but it's a definite change with this example. It's not quite as straightforward as the other ones, because the change in this one is going to be when we rotate. We're not going to just be rotating. We're going to still be rotating about a horizontal axis, but it's not going to be the x-axis. So rotating about a horizontal axis, but not the x-axis. Okay, everything we've done so far, we've been rotating specifically around the x-axis. So suppose we don't want to rotate about the x-axis, we want to rotate about some other horizontal axis. It's not that much more difficult, but you need a good picture to get an understanding then of what your radius is going to be. What this does is it makes it a little more difficult to find radius. Okay, not hard, but a little more difficult to find the radius value. Okay, so I'm going back to the textbook where we can get a diagram of this. We're going to be looking at example 6 on page 311. Okay, let's just read it. It's the very last sentence on the page. It's it. Find the volume of the solid generated by revolving the region bounded by y equaling square root of x and the lines y equaling 1 and x equaling 4 about the line y equaling 1. Okay, I'll write all these words down because you have to look at it. You have to read it a couple of times to understand the question alone. Okay, so here's what it says. It says find the volume of the solid generated. Find the volume of the solid generated. You didn't find the volume of the solid generated by revolving the region bounded by y equaling the square root of x and the lines y equaling 1, x equaling 4, and about the line y equaling 1. Find the volume of the solid generated by revolving the region bounded by y equaling the square root of x and the lines y equal 1, x equaling 4, and about the line y equaling 1. Okay, so what this is saying is your region is created by the lines y equaling square root of x, y equaling 1, and x equaling 4. So you're going to create the region with these three pieces of information. Once you've created this region, then you're going to spin it around y equaling 1. Okay, so this is the axis of rotation. Okay, you're spinning it around y equaling 1 after you created the region. So let's see if we can figure this out. Okay, so we have y equaling the square root of x. And you have y equaling 1 and x equaling 4. Okay, here's my x equaling 4, which is a vertical line. Okay, this is x equaling 4. Here's my y equaling 1, which is my horizontal line. And here is my curve. Like that. Well, actually the curve keeps going. So the region bounded by the curve y equaling the square root of x and the lines y equaling 1 and x equaling 4. What does that region look like? Where is that region? Y equaling 1, x equaling 4, and y equaling the square root of x. Y equaling 1, x equaling 4, and y equaling the square root of x is this region right here. That's the region we're spinning. Now we're not spinning it around the x-axis, we're spinning it around y equaling 1. So we're spinning it around this guy. So this is what it's going to look like right here when we start spinning it. Right? This is my spin zone. Okay. So now, if you're spinning it around a horizontal axis, you must integrate with respect to dx. If you're rotating around a horizontal axis, you're going to integrate with respect to dx. So this is going to be your area, dx. I've been using capital A. I should make that a capital A. Now, your bounds, your upper and lower limits are going from here to here. The point here, the point, the vertex, and this point here. Now I can tell you the upper x number is 4, right? But what is this one? It's not 0, is it? What it is? Something here, somewhere in here, and this number 4. What is this? So we have to find this ordered pair here to know what that x value is. How do I find that ordered pair? It's an intersection of y equaling 1 and y equaling the square root of x. So to find where they intersect, I set the square root of x equal to 1, so what must x be? 1. So this is the ordered pair 1. It's actually the ordered pair 1, 1, right? So my left bound for this region, for all these little wedges, all these little discs I'm cutting out of the middle of this thing, I'm going from an x value of 1 to an x value of 4. So it's going from 1 to 4. And this is going to be a pi r squared dx because the area of the face of every one of those discs is a circle whose area is pi r squared. So now the r has to be in terms of the x variable. Now you got to visualize what is r. This is kind of the big deal. This is r. This region that I'm highlighting, that's your r. There you go. So this ordered pair on this line, y equaling the square root of x, is x square root of x. So r is a height of the square root of x. Not exactly, right? Okay. All of this region is a height of square root of x. This region here, yeah, this is so hard to diagram it, is therefore what? Minus 1. It's the whole square root of x minus the part 1. The whole square root of x minus the part 1 gives me this region, which is the square root of x minus 1. What a mess! So your radius is the square root of x minus 1. So you're going from 1 to 4 of pi times the square root of x minus 1 squared dx. Okay? All of this is the square root of x, but you've got to cut out the 1 to get the true radius of the wedge. And there it is. So then you'll integrate from 1 to 4 of pi times what? X minus 2 square root of x plus 1 dx, which is not a difficult integration. And so after you've had a little work on doing that, you'll come up to the fact that this becomes 7 pi over 6 cubic units. Okay? So when you have something being rotated around an axis that is not your x-axis, you've got to pay a little more attention to what the r value is. 7 pi, it's not on there, is it? My camera won't pick it up. 7 pi over 6 cubic units. Okay, so again, there's emphasis on the change, is that there's a little more difficulty in finding r because you're not rotating around the x or y axis. Okay, now the next one's a pretty big change. Call it big change, okay? Big change, okay? This one's different. This is going to feel a little awkward, okay? We've been rotating around a horizontal axis. Now we're going to rotate about a vertical axis. Okay, rotate about a vertical axis. When you start spinning around a vertical axis like a y-axis, then when you calculate your volume as being your area times your width, which is our pi r squared dx, when you start doing this, it changes when it's around a vertical axis, and then it's no longer x, it's going to be dealing with y. So your area must be in the y variable, and your r must be the y variable. So you start spinning around a vertical axis, all of your variables must change to y. So this is horizontal axis business. This is vertical axis business. And so it's a little bit awkward. Okay, but you have to nail in your mind, I've got to play in the y variable, not x. I've got to work with the y variable. Okay, so let's take a look at example 7, which is on page 313 of our textbook. Okay, here it is. It says, find the volume of the solid generated by revolving the region between the y-axis and the curve x equaling 2 over y, where y is running between 1 and 4, and rotate it about the y-axis. So I will write this down. And it says, find the volume of the solid generated by revolving the region between the y-axis and the curve x equaling 2 over y, where y is running between 1 and 4, and you're going to rotate it about the y-axis. Okay, so you're going to create the region that you're eventually going to rotate. You're going to create the region between the curve y equaling or x equaling 2 over y and the y-axis. That's going to give you the region to rotate. And when you get ready to rotate it, you're going to rotate it again around the y-axis. Okay. What in the world does x equaling 2 over y look like? If I have to graph x equaling 2 over y, and I make a table, well, if I'm going to run from 1 to 4, okay, yeah, you could do it the other way too. If I'm going to run from 1 to 4, maybe I should do, whoops, if I'm going to run from 1 to 4, I want my y to be a 1 and a 4 value. So if y is 1, x is 2. If y is 2, x is 1. If y is 4, x is a half. Those are some ideas to get it graphed. So how big do I want these tick marks to be? I can go all the way up here. 1, 2, 3, 4, 5, 6, 7, 8. So if I go 1, 2, 3, 4, there we go. And then 1, 2, 3, 4. I'm trying to make it big enough so the graph is pretty good. Okay, so I've got the point where x is 2, y is 1. Where x is 1, y is 2. Where x is a half, y is 4. There you go. Okay, now find the volume of the solid generated by revolving the region between the y-axis and the curve. So between the y-axis, this y-axis, and that curve, that region then equates to this. Okay, there's your region. Now it says rotate it, spin it around the y-axis. Right here. It'll look something like that when you start spinning it. So all of your discs are going to look like this. Really the base, if you want to try to get a better vision of it, it's going to look kind of circular. That is kind of your object that you would create when you start spinning this thing. Okay, there it is. Okay, so you got to remember, we're rotating around a vertical axis. So if I'm rotating around a vertical axis, I have to integrate with respect to y, which means everything has to be in the y variable. My upper and lower limits must be with respect to y variables. So what are my upper and lower limits here? There you go. This 1 and this 4. From 1 to 4 in the vertical direction, the y values are from 1 to 4. So this is going to be area, which is going to be pi r squared. Now this r must also be in the y variable. I have to rewrite r as an expression involving y. Well, this is your, if you look at this one slab or this one disc cut out, this is your r value then. Okay, that horizontal line is your r. So you need to know this ordered pair right here. Now in terms of x, well I don't even know if I can write it in x. In terms of y, here we go. This is the ordered pair xy, right? So this is going to be 2 over y, where x is replaced by the 2 over y. That ordered pair is 2 over y. The r, which we've just drawn, or I just drew, is going to be the first coordinate of this ordered pair, right? This horizontal distance is the first coordinate of this ordered pair. horizontal distance, first coordinate of the ordered pair. So this r is 2 over y. So you're integrating from 1 to 4 of pi times 4 over y squared dy, which is really just 4 pi integrating from 1 to 4 of y to the negative 1 dy. This will not be difficult to do, and your result will be 3 pi. Which will give you the volume of that solid. Yeah, we'll fix that. Sorry about that. Thinking y to the negative 2. Okay, one more example, and then we'll take a break. Give you all a break. Let's get through another example, because if we can just do one more example, then we'll break on a nice transition to another topic. Okay, so one more example, and then we'll break. We're going to continue to rotate. In this example, we're going to continue to rotate about a vertical axis. Anytime you're rotating about a vertical axis using the disk method, remember you're going to integrate with respect to dy. Okay, you're talking dy. You've got to be certain you make that transition. So we're going to look at example 8 on page 313. And what it says, I'll just write it. Find the volume of the solid generated by revolving the region between the parabola x equaling y squared plus 1 and the line x equaling 3, that's your vertical line, about the line x equaling 3. So when they say about the line, that means you're revolving around, you're revolving around the line x equaling 3 also. Okay, so let's try to graph it. Come back. Okay, so you have a parabola. Well, here, the line x equaling 3, I'm going to put it in. Here's your x equaling 3. This is what you're revolving around. It's also part of your boundary of your region. And we got to graph x equaling y squared plus 1. Well, when you graph x equaling y squared plus 1, that's a horizontal parabola shifted right 1. Okay? So it's going to have a vertex at an x value of 1. So it's going to look, I don't know, something like this. So your region that you're rotating is bounded by the parabola and the line x equaling 3. So it's this region right here. This is the region you're rotating. It's a little more symmetrical with respect to the x-axis, but that's it. You're rotating it around x equaling 3. So when you start spinning it here, it's going to look like, well, it's going to be more rounded. It's going to look kind of like a football. Okay, you're going to come up with this thing that looks something like a football. Let's probably not that pointed on the ends, really. And so your disc that you're going to slice out of it looks something like that one. Okay, so when you integrate, you're going to be integrating pi r squared dy. You're going to have to figure out what r is in terms of the y variable, and your upper and lower limits must also be y values. So let's just talk about your upper and lower limits of integration. You're going from here, the point of intersection under the x-axis, to the point of intersection above the x-axis. Those are your y values that these slabs are being sliced inside this football from like bottom to top. So you know this ordered pair, if this vertical line is x equaling 3, this x value must be 3, and therefore the y value would be what?
Square root of 2.
Very good. And this, well, that's a negative 3. No, it's not. It's positive 3. A negative square root of 2, right? Okay. And this is going to be positive 3, positive square root of 2. So it's a negative square root of 2. So you're going from a negative square root of 2 to a positive square root of 2. And that was found by using your equation. So if you put an x value of 3 in, then y will equal plus minus the square root of 2, which is the lower and the upper limits of your integration. So you're going from negative square root of 2 to positive square root of 2 of, again, pi r squared dy. Now we've got to figure out what r is. R is from here to here. This is your r. Okay. This ordered pair on the curve, every ordered pair on the curve is x, y. But everything must be in terms of the y variable. So you replace that x with y squared plus 1, y. So what is the length of r? Very good. It's 3, okay? It's this entire distance, right, is 3. So you're taking the 3 minus this amount to get this amount, right? The whole minus the part. The whole, which is 3, minus the part. So your r is the whole length of 3 minus this distance, dashed line distance, which is y squared plus 1. The whole of 3 minus the part y squared plus 1. So your r is 2 minus y squared. The whole is 3 minus the part, which is y squared plus 1. So now what you're doing is you're integrating from a negative square root of 2 to a square root of 2 of pi r squared, where r is 2 minus y squared squared dy. And when you integrate this, you can pull the pi out front. And when you expand this binomial, it'll be 4 minus 4y squared plus y to the 4th dy. And then this will end up equaling 64 pi times the square root of 2 over 15. I should have put approximately. That is what it will equal, cubic units. Okay, so now let's take a break. We've done the disc method. We've done the slicing. We've done 2/3 of the section. What we have left to do is what we call the washer method. So I'm going to pause the recording and give you a minute now to go take a break. And we'll come back and finish this. Okay, so let's turn this recording back on. And I'm going to go back for just a minute because there seems to be a little bit of confusion just by the expressions on your face before a break. If you have a distance that you're looking for, say you have from 5 to 3. If you're looking for the distance between 3 and 5, it's very simple. You say it's 2, but it's calculated by saying 5 minus 3, which is the whole minus the part. Okay, the whole minus the part. The 5 minus the 3 is the whole minus the part. So like in that last example, we had a value out here of 3 and a value in here, which was not a number, it was y squared plus 1. And we wanted to know this distance between the y squared plus 1 and the 3. So it's determined by the whole, which is the 3, minus the part, which was the y squared plus 1. Okay? So to find that distance, as we did in that last example 6, it was the whole distance of 3 minus the empty distance of y squared plus 1. So to find this r, we took the 3 minus the y squared plus 1 to get this distance r. And understanding that's pretty important as you're integrating with all these solids that you're revolving around these different vertical or horizontal axes. Okay, so it's all minus part, just trying to get a better image of that. Okay, so now let's go into the next section. The last, pretty much the third concept of this section, I should say, which is still working with solids of revolution, meaning revolving around some axis to get a three-dimensional object that we're going to find the volume of. But solids of revolution, I'm going to call this part 2. And in this case, it's no longer the disk method, but now it is the washer method. Okay, the washer method. No longer the disk method. Now we're going to transition into the washer method. Okay, so if you just think about disks and washers, this is a disk. It's a solid circle is a disk. A washer is one in which it has a hole in the middle. So if you're looking for the area like a donut, okay, this is like a donut. A washer is similar to a donut, but it's flat. So you have an outside radius of capital R and an inside radius of little r. So to find the width of the donut hollowed out, or the width of the washer, you're looking at capital R squared minus little r squared. Now I've got to rearrange this. If you're looking for the area of the washer, it equals the area of the disk minus the area of the hole in the middle. The area of the solid disk minus the area of the hole. So this is pi capital R squared minus pi lowercase r squared to find the area of the washer. Okay, to find the area of the washer, which is like the donut, this region here. This is the washer. So big minus little, or outside minus inside, is really how they refer to it in this textbook, is the area of the outside minus the area of the inside. Now when you convert this to volume, okay, when you convert it to volume, you're going to be integrating, say, from A to B, of your area times your width, which is like d of x, which is approaching 0, of each one of these washers. So as you convert this to a washer, your area becomes pi capital R squared minus pi little r squared dx. So when you're finding the volume of a washer, you're taking the area of the outer disk, really minus the area of the hole, in order to get the volume of the washer times the width. Now they show this in the textbook using capital R's and little r's, but remember these r's are your radius in terms of the x variable. So to make it more official, when you find volume, you're integrating your area times the width of each one of these little disks. So this is really pi r of x squared minus pi little r of x squared dx. because that takes it revolving it around a horizontal axis. So it's just a little more difficulty added to the disk method, but not really bad. Okay, so if you want to kind of keep this organized, you can call this kind of the warm-up to the washer method. They have an image of this in our textbook, which is done quite nicely, where you put a hole in the middle of your object. This is on page 314. Here's a strange-looking object. We just kind of did an example like this, but here they're putting the hole down the middle. They're making it hollow. Okay, it's a washer instead of a disc. So you're going to be looking at two curves like this. The area between the two curves spun around an axis will leave a hole down the middle. Leave it hollow. Okay, so that's a pretty good diagram. Then again, they're kind of talking about the outer radius and the inner radius. The outer radius minus the inner radius, then kind of creating the hole in the middle, creating the washer. And here's where you see the notation of the capital R of X. Instead of just capital R, it's really R of X, so you're staying in the X variable. The inner being the little r of X, squaring it, and then coming down to the area, or to the volume, I'm sorry, by integrating the area, giving this formula which I just wrote. Okay? Now, something you must be very careful of. It's a common mistake, and even I have to be very careful when I'm doing these that I don't make this mistake. You square the radius of each one independently of each other. This is not the same thing as R of X minus R of X squared, okay? This is not correct. It is not the same thing. This is correct. You square the radius times times pi. You square the radius times pi. You don't subtract the radius and then square it. This is wrong. Okay? Be very careful that you don't take the subtraction and after it's subtracted you square it. You square it before you subtract. So be very careful with that you don't make that mistake. Okay, so let's do an example. Okay, look at example 9. I don't know how I have my page numbers so messed up. Page 314. Okay, it says find the region bounded by the curve y equaling x squared plus 1, which is a parabola up 1 unit, y equaling x squared plus 1, and the line y equaling negative x plus 3. That's just a linear line. Okay, so you're going to graph a parabola and a straight line. They're going to most definitely, I guess, intersect somewhere. You're going to take that area between these two, that region between these two, so take the region bounded by the curve and the line, and revolve it about the x-axis. To generate a solid. A solid with a hole in the middle, which makes it a washer when we take slices of it. Find the volume of the solid. Okay, so we're going to have to figure this out. We're going to have to graph this thing. Okay, so we have y equaling x squared plus 1. I don't know how big to make this. I better go to oh crud. 1, 2, 3, 4. Okay, So y equaling x squared plus 1 starts here, go to here, like this. And so here's your parabola, or something like this. It's not going to be, I don't have it perfect, so I'm doing it pretty quickly. Here's our parabola. And then we have the line y equaling a negative x plus 3. So it's up here, and it's looking more like this. Now don't just look at my points of intersection as if they're on, because they're probably not. Okay. So there is your x squared plus 1. It's a parabola up 1 unit. And your y equaling a negative x plus 3, which is a straight line, slope of negative 1, and a y-intercept of 3. So the region you're looking at is this right here. Oh, did I do it backwards? I did do it backwards. It's supposed to go this way. Ah! Yep, listen to him. Yep. Man. Okay, try it again. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, and 2, 4. Well, if I could use a pencil and it would project well, I would. Watch me do this wrong again. Let's get ready to do it wrong again. Something like this. Okay. It's not as pretty as the other one. Not anywhere near as pretty as the other one. Something like this is the region bounded. Okay, we're supposed to be revolving this about the x-axis. So if we're revolving it about the x-axis, then we're integrating with respect to dx. And what we're integrating with respect to dx is a washer. So what we're doing now is we're going to integrate the outside area of a disk minus the area with a little r of the hole in the disk with respect to x. And these r's have to be converted to an expression in the x variable. Now, to find the upper and lower limit, I have to determine these points of intersection, because you're going to go with respect to dx from whatever this value is to the left, moving to the right. So what are the points of intersection? Well, my two graphs were of x squared plus 1 and of negative x plus 3. So to determine where they intersect, I set them equal to each other. Then I take that and set it equal to 0. Factor it. Oops, that's a minus 1. And I come up with a negative 2 and a positive 1. So evidently, this is the point, negative 2 something, and this point of intersection is 1 something. So then you just plug it into one of the two equations to get the full ordered pair. So this would be a 5 in my vertical value, and when x is 1, y would be 2. So there's your 2 points of intersection. So if you're integrating now with respect to dx, this is an x dx stuff, then your x value on the low side is a negative 2, and your y value on the high side is a 1. So you're integrating from negative 2 to 1. Now, you're spinning this thing around the x-axis. Oh, my. Oh, dear. This is really not easy for me to do. So it looks something like this when you spin it, right? That's pretty good. Looks something like that when you spin it. So you're going to have a disk here, or a slice of this volume while this thing is spinning. Okay, so try to think of this as your outside disk and your inside, or your outside circle and your inside circle. So when you integrate, your R of your outside is from here all the way up to here. This is your capital R. Now this ordered pair is going to be X. What's the vertical value in the terms of X of this ordered pair? This ordered pair. Negative X plus 3. That's going to be the name of every ordered pair on that straight line. The ordered pair on the parabola is going to be X and what? X squared plus 1. There's your two ordered pairs. Your outside radius is the long one, which is going to be what? There you go. Your negative X plus 3, and you're going to square it. Your inside one is the shorter one, which what is this height right here? There you go. And there it is. Your pi capital R squared, where capital R is a negative X plus 3 being squared, and your pi little r squared, where your little r is the X squared plus 1 being squared. Now you could have pulled the pi out if you wanted to. And this is going to be what? X squared minus 6x plus 9 minus x to the 4th plus 2x squared plus 1, all dx, from negative 2 to 1. So this is pi from negative 2 to 1 of a negative x to the 4th minus x squared, right, because it's a minus 2x squared plus x squared, minus 6x plus 8. I think I did that right. And when you integrate that, it takes a little time, you're going to come up with 117 pi over 5 cubic units to be the volume of that figure. And here's a picture of it. I can pull a picture of it out of the book. It's still kind of hard to get the image of it. Even with this gorgeous picture of this thing. Okay, there's our two-dimensional view of what's getting ready to get spun around the x-axis. Here it is spinning. So it gets really thick here toward the middle. It gets really thick just on the negative side of the origin. Really thick. And then it thins out and opens up. Kind of reminds me of these things like the Children's Museum where it's big and you take the penny or whatever, you sit on that side and it rolls around, 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 and it falls down the middle. Something like that. Okay, kind of a hard thing to get a vision of. Okay, let's try another one. Look at example 10 on page not 404, page 315. I don't know, can y'all go in and print these pages out of the textbook on the electronic version? The region bounded by the parabola y equaling x squared and the line y equaling 2x in the first quadrant. Okay, bounded by the parabola y equaling x squared and the line y equaling 2x, and in the first quadrant, is revolved about the y-axis. Okay, real quick, you see that? Revolving about the y-axis. This is going to be a dy. Okay, it's going to be a dy situation to generate a solid. Find the volume of the solid. Well, once you see that revolving about the y-axis, your mind should trigger, oh dear, it's a dy thing. Everything has to be in the y variable. I've got to kind of twist everything to the y variable. Okay, let's see if I can graph this one correctly. Okay, so the parabola y equaling x squared looks something like this. I'm not even going to try to plot points. I'm just going to throw it up here. And the line y equaling 2x. Something like that. And it must be in the first quadrant. Voila. There it is. This region right here. Spin that thing around the y-axis. So when you start spinning it, not exactly a funnel, but spin it around y. So if you cut this little wedge, not wedge, if you cut this little washer out of this thing, it would be hollow like this. Okay, so this integration is happening with respect to dy. This could be an outside disk minus an inside hole. So you can think of it a pi capital R squared minus a pi little r squared, where all those r's are going to have to be converted into the y variable. Now, what's my lower and upper limit on this thing? Well, to find that, it's y. Okay, be very careful. These are y values. So 0 to something, remember this is a y value. Got to figure out what that point of intersection is. So where in the world is the point of intersection of 2x and x squared? So set them equal to each other. And we're going to come up with an x equaling 0 and an x equaling 2. So this point here is the point 2, 4. Okay, remember, this is a real room for mistake right here. It's tempting to put from 0 to 2, but that is not right. These are y values. So it's from 0 to 4. Your y values, you're sliding up and down the y-axis, so you're going from 0 to 4. Okay, so the radius of the distant curve right here, which is your capital R, this is point xy, but in terms of y, this is your parabola. What is this? If you have y equaling x squared, then x equals the square root of y, right? So this is the square root of y. Because everything has to convert to the y variable. So now, what is your capital R? From here all the way out, there you go. Capital R is the square root of y being squared. Capital R is the square root of y, the horizontal distance to the outside of the disk. Now, this point right here also has an ordered pair, x, y, but it all has to be in the y variable. So when you say y equals 2x, then y divided by 2 is x. So replace the x with y halves. So it's y halves y. So what is little r's value? Y halves. So this one's pi y halves squared. All of this dy. So this is the outside circle, which is really the disk, the area of the whole disk, minus the inside circle, which is really the area of the hole. And to convert it all to volume, you take the areas times the width of each one of those disks, which is approaching 0, which will therefore give me the volume of that solid spinning around the y-axis. So without doing the whole thing, this is 0 to 4. You can pull the pi out front. This would be y minus y squared over 4 dy. It wouldn't be that difficult. And this turns out to be 8/3 pi cubic units. The volume of that thing spinning. And it would hold a liquid or any kind of substance because there is not a hole. Well, here's a much better vision of it. There it is. Well, it's not really perfect. A little orange donut. That's what it looks like. With all this lovely knowledge on it. Okay, do not shut me out because I'm going to do a summary. We're through with examples, but I want you to think for just a minute about what we've done. We've done a lot. We started out by simply doing what they called slicing. This was those examples where you weren't revolving a thing, okay? This was just a three-dimensional object like that pyramid where you were finding the volume of it. So you were integrating area times width, but there was no revolving going on. You were just taking the area of a slice times dx, integrating it and getting the volume. That's all there was to it. No rotation. Okay, this was no rotation. They gave you a three-dimensional object. Okay, they just gave you a three-dimensional solid, and they said, figure out what the volume of this thing is using integration. Then we started rotating. We started rotating about a horizontal axis and a vertical axis. There were two methods. There was the disk method, which was just pi r squared stuff, and then there was the washer method, where there's a hole in the middle, which is a pi r squared minus a pi r squared. Be extremely careful. In all cases, in rotations, if you are rotating around a horizontal axis, then you're integrating with respect to dx. Everything must be in x. If you're rotating about a vertical axis, then everything must be in y, including the upper and lower limits of integration. So you have to be very careful. When we go into y'all need to kind of do this work before you come back on Wednesday, because when we go into the next section, this turns on us, okay? When we're rotating around horizontal, it's dy, and rotating around vertical, it's dx. So you got to land this before we go into the next section because it's going to put a spin on it all. So y'all play with that. I'm going to go to my office and get your homework written and posted. And I will see you on Wednesday.